Welcome to the Deep Dive. Today, we're taking a deep cut into a framework that, honestly, aims to eliminate one of the biggest engineering headaches in machine learning.
Oh, for sure. Deploying stateful models.
Exactly. We're talking about data flow. We've gone through a pretty dense technical paper on it, and our mission for you is to walk away understanding its architecture, what it formally guarantees, and why it's such a big shift from the usual way we do MLOps.
I think we have to start where they start.
The foundational problem.
Right. This conceptual rift, really, between how we develop models and how they run in production.
Every data scientist starts with a nice, clean, static data set.
Mm-hmm.
But production isn't like that.
No, production is just this unbounded, continuous flood of data. You've got sensor data, financial quotes, logs. It never stops.
And the paper calls this the fallacy of finite data. I love that term. It's the root cause for why so many production systems just, break.
And that fallacy forces teams to do something that seems logical. You discretize the stream. You chop it into batches.
But that's where the technical debt begins.
It's massive. And the authors are really systematic here. They identify four main categories of failure that come directly from that one decision.
Okay, so what's the first one?
The first is something I think a lot of us have run into: batch boundary artifacts.
These are so insidious because they're almost impossible to replicate. You mean things like a rolling 90-day average?
Exactly. A stateful operation like that, it works perfectly in your backtest.
But in production, the way the data is partitioned, where those batches arbitrarily start and end, is totally different.
And suddenly the calculation is different, the computation becomes dependent on the batch size, and your backtest is, completely useless.
Which leads to the second failure, and this one is, I think, catastrophic for performance.
Causality violations. Absolutely.
Future peaking.
Future peaking. When you process a whole batch at once, you have this illusion that you have all the data from, say, 9 a.m. to 5 p.m. simultaneously.
So it's incredibly easy for a calculation you're running at noon to accidentally grab a piece of information from 4 p.m.
Right. And your model looks like a genius.
In development. Only to completely fail the moment it sees data one tick at a time. It's one of the hardest bugs to find because the backtest results just look so good.
And then you get into the pure engineering failures. Number 3 is development production divergence.
The classic handoff problem. You prototype something fast and easy in Pandas or scikit-learn on your laptop.
And then you throw it over the wall to an engineering team, and they have to do a complete ground-up rewrite in something like Flink or Spark streaming.
Which introduces massive delays and, more importantly, the risk that their implementation isn't semantically identical to your model.
For sure. And what happens if something goes wrong in that complex distributed system?
That's the fourth failure. Limited reproducibility. Trying to debug a production glitch is agonizing if you can't just replay the exact state that caused the error.
So DataFlow is designed as the answer to all 4 of those problems.
Its main goal is a unified computational model. Right? One that makes it trivial to get a research prototype into production.
Trivial is the goal. It means you process historical batch data and live streaming data in the exact same way.
And crucially, no software rewrite between those two stages.
That's the promise.
Okay, so if the goal is that level of fidelity between batch and stream, they must have a really rigorous way of achieving it. Let's dig into the architecture.
It starts with the data model, which they call the stream data frame.
Which is pretty intuitive. It's just an unbounded time index table, and the computations are organized as a DAG, a directed acyclic graph.
But the rigor, the real secret sauce, comes from their definition of correctness. For any of this to work, a computation has to be tileable.
Okay, let's unpack tileable. Does that just mean you can cut the data into chunks? Or is there more to it?
There's a much deeper requirement. It's about preserving correctness when you partition the input.
So if I have 2 days of data...
Right, and you process it all in one go, you get a result. Now, if you slice that same data into, say, 4 12-hour tiles and process them one after another...
The final combined result has to be mathematically identical to the first one.
Identical. The result has to be invariant to the partitioning.
That makes sense. And that property, that tileability, seems to hinge on what they call point-in-time idempotency.
That is the central formal guarantee. It's a bit technical, but the idea is simple.
Lay it on us.
The output generated at any specific time, let's call it t, must depend only on a fixed, finite history of data right before t.
So there's a specific window of data that matters, and everything before that is irrelevant for that specific calculation.
Precisely. They formalize this as the minimal context window length, L. As long as you give the system an input batch that includes at least L time steps of history before T, the output at T is guaranteed to be the same.
So let's make that concrete. A simple 10-step moving average.
Okay, so L is 10.
If I run my backtest on a year of data, the calculation for today uses the last 10 data points.
Right.
If I run that same model in a live stream, the result for today will be identical, as long as the streaming engine has kept those last 10 points in its memory, its context.
That's the idempotent guarantee. Anything before 10 minus 10 is completely irrelevant to the output at T.
And once you have that, the architectural benefits just start cascading.
They really do. First, obviously, you get the unified batch and streaming execution that you wanted.
And second, it enforces causality. The system knows exactly how much history it needs, so it can't accidentally peek into the future.
Third, and this is huge for operations, you get memory-bounded computation.
Because you know you never need to load more than L steps of state into memory for that node.
Exactly. Even if the total dataset is petabytes, your memory footprint for that one calculation is fixed and known. A massive win.
And fourth,
Deterministic replay. Because the state needed for any output is finite and known, you can debug systematically. You just replay the exact input data.
and the system guarantees you get the exact same bug.
Right. It turns debugging from a 5-hour random walk into a simple deterministic exercise.
Okay, so let's get into the nuts and bolts of the DAG. How is the data actually structured inside DataFlow?
They're very specific here. They mandate a wide multi-index format.
Time is the main index.
Right. Then features on the outermost column index, and then assets or entities like stocks or sensors on the innermost index.
And for the experts listening, the reason this is so important is efficiency. It aligns perfectly with how libraries like NumPy and Pandas want to see data.
You get automatic vectorization. If your calculation is independent across all your assets, you can run it on all of them at once with a single instruction.
Effortless speedups.
Now let's go back to causality, but with their specific terminology. They distinguish between event time and knowledge time.
This is critical in the real world. Event time is when something actually happened.
And knowledge time is when your system found out about it. The wall clock time of arrival, they are not always the same.
Right. In finance, a stock quote might have an event time of 9.3 or 9.05, but it only hits your server at 9.3.08 because of network latency. That's its knowledge time.
Exactly. So if you're making a decision at 9.3.07,
You cannot possibly use that quote. Even though its event time is in the past, its knowledge time is relative to you in the future.
and DataFlow enforces this strictly, a node running at simulation time sim is physically prevented from accessing any data point whose knowledge time is greater than sim.
That's how they kill the future peaking problem at the framework level.
It makes those simple but wrong tricks you can do in a backtest like using an index shift to get tomorrow's price completely impossible. The kernel just won't allow it.
So we have these causal nodes. What happens when you start chaining them together into a DAG? The context windows must accumulate somehow.
They do. They formalize this as the path context window. If you have a path, V1 to V2 to V3, and each has its own minimal context, L1, L2, L3.
The total history needed by the final node V3 isn't just a simple sum.
No, it's not. The paper gives a formula, but intuitively the context of V2 is relative to the output of V1. The overlaps are handled correctly.
So if the windows are, say, 2, 3, and 2, the path context ends up being 5, not 7.
That's the example they use. And now, for the most critical parameter in the whole system, the graph context window, which they call WG.
Which is just the maximum of all those path context windows across every single path from a source to a sink in the deity.
It's the longest chain of memory dependency in your entire computation.
And this number, this WG, dictates your execution tile size. The paper proves that tau has to be greater than or equal to WG. Why is that mandatory? What breaks if you pick a tile size that's too small?
If tau is less than WG, your computation will silently fail right at the tile boundaries.
How so?
When the system goes to process the next tile, it needs WG steps of history to compute correctly. But it only kept sets of lookback from the previous tile.
So the required state isn't fully available across that boundary.
And the output you get from your tiled backtesting execution no longer matches what you'd get in a true streaming execution. Your backtest is, again, invalid.
So the WG isn't just a suggestion for efficiency. It's a hard requirement for correctness.
Absolutely. Now, on execution, the DAG structure is great because it exposes all your potential parallelism, but it also defines your limits.
This is the critical path latency lower bound.
Yes, a theorem that basically says your minimum possible end-to-end latency L, is set in stone by the longest sequential path of dependencies in your DAG.
And this is where the rubber really meets the road for performance. L is the sum of the processing times for every node along that one single longest path.
It's a hardware-agnostic bottleneck.
Right. You can throw infinite GPUs at the problem, but if you have 10 nodes that must run one after another and each takes 10 milliseconds,
Your latency will never be less than 100 milliseconds, period. If you need 50, you have to change the model architecture itself, not just buy more servers.
so your performance limit is baked into the model design.
It is. But DataFlow does leverage other kinds of parallelism, non-temporal parallelism, through what they call Columbar tiling.
Which is really just spatial tiling.
Right. And this goes back to that multi-index data format. If the calculation for, say, asset A is totally independent of asset B,
You can partition your columns into groups and process all those groups completely in parallel.
but, and this is a big but, that strategy is constrained by any cross-sectional operations.
Like if you need to rank all 5,000 assets at one point in time.
Or normalize a feature across the entire cohort, that forces a synchronization barrier. The system has to stop, wait for all the column tiles to finish, execute that one cross-sectional step, and then it can parallelize again.
Okay, so let's look at the simulation kernel that manages all this. The paper describes it as a series of nested loops. It's quite a hierarchy.
It is. At the very top level, you're managing multiple DAGs, maybe for a big hyperparameter sweep.
Then inside that, you have the learning patterns, like a fit followed by a predict.
And beneath that, you get to the core execution, the temporal tiling loop, then the spatial tiling loop, and finally at the very bottom, you execute a single DAG tile topologically.
That systematic structure is key for the MLOps side of things.
Yeah.
They use a structured config object to define the entire system.
And that config maps perfectly to the system being run, which makes every experiment traceable and reproducible.
Which is then supercharged by their automatic caching.
Right. The output of every single node is memoized with a hash key. And that key is a composite. It's a hash of the node's inputs, its specific config, and the actual source code of the transformation.
The power there is in those huge parameter sweeps. If I'm running 100 experiments, and they all share the first 5 feature engineering steps.
DataFlow calculates those steps exactly once. If the hash key is identical, the result is pulled from cache. It saves a massive amount of redundant computation.
And finally, deployment. How does a trained model actually get into production?
It follows the scikit-learn semantic. Stateful nodes, like a trained model, have a fit method and a predict method.
So you run fit on your training data.
And the entire fitted DAG with all its learned state and its context requirements can be serialized into a single artifact.
Which you can then package up maybe as a Docker container and hand off to something like Airflow to schedule and run against the live stream. When you look at the whole landscape, Flink, Spark, Feature Stores, DataFlow really seems to carve out its own unique space.
It really does. It sits at this crucial intersection of serious stream processing and the specific needs of machine learning. No other framework really combines its 3 formal guarantees:
Point-in-time idempotency,
causal safety,
and unified batch stream backtesting.
all in one environment that's built for the data scientist, not just the data engineer.
And that integration is what's designed to eliminate that huge engineering debt we talked about at the start. It forces the rigor up front, so your prototype is already a production-ready system.
The translation step effectively disappears.
Okay, so we've established that the graph context window, WG, is the proven minimum tile size you need for correctness. But we want to leave you with a final thought, especially when you think about real-world production systems.
Many fundamental nodes we use, things like an exponentially weighted moving average, are technically infinite impulse response filters. They have infinite memory.
For practical use, we have to truncate them. We say, okay, we'll keep 8 steps of history, and we'll accept some tiny error tolerance epsilon.
Right. We accept a result that's maybe only 99.999% of the true infinite result.
So here's the thought. If your individual node context windows are based on this subjective tolerance-based truncation, how complex is it to rigorously estimate the true WG for a huge, messy production day viewer?
And more importantly, how do you manage the trade-off? You want the smallest possible tile size for the lowest latency and fastest throughput.
But to guarantee correctness, you need a tile size that is robustly larger than that subjectively defined WG. It forces you into a really tough operational decision between raw speed and certifiable stability.